Well, we're going to be talking about related rates in this section of videos here. Um, and of course, we're going to get started with an example immediately. Let's say, for example, I have y is equal to x squared. Okay, so we've all probably seen that. And I want to find dy over dt. And we're going to be given, so they're going to give us, let's say for example, dx over dt, and we'll say that that happens to be 1. And also, x is equal to, let's say, 5. Okay, so this is how this works out. So when I take the derivative of y here, it's 1, okay? Derivative of y is 1, but then I'm going to write dy over dt. Now I'm going to take the derivative of x, this time with respect to t. The derivative of x squared is 2x. But now I'm going to write dx over dt next to it. Okay? And now we're given dx over dt is 1. Well, first I might as well write 5 in here. And dx over dt is 1. And so this is equal to 10. dy over dt, okay, that's supposed to be a y there, is equal to 10. Now this t is normally in time. We'd be using time here. So this is some distance over time. So this would be like, feet over seconds or something of that nature. But this is normally the setup of how we work a related rate problem. And sometimes we got to actually construct this piece right here. So when we work our application problems, we're going to have to come up with this guy right here. And okay, so let's look at another one. So let's say that we have y is equal to 1 over the square root of x, and we want to find dy over dt, and we're going to be given dx over dt is equal to 3, and when x is, let's say, 6. So we want to take the derivative of this, but first off I'm going to have to rewrite this. This is x raised to the negative a half. Now this is x to the half, but I'm going to go ahead and take it up into the numerator. So we take the derivative of y and we get 1. So we're left with dy over dt. We take the derivative of x, and so we end up with bringing that negative a half out front, subtracting 1 from that. So it's going to give us negative 3/2. Right, and then I got to write dx over dt. And then all I do now is go ahead and I plug my 3 in, and I plug my 6 in right here, plug my 3 in right here, and we are finished. We have now found dy over dt. And so this can be rewritten as 1 over 2. I'm going to go ahead and plug my 6 in. This is 6 raised to the 3/2 times, I didn't leave much room for me here. It's okay, I can get it, over dy over dt. Right? It's supposed to be a 3 there. Anyway, so I'll let you figure out what all that's supposed to be. But those are the steps of a simple related rate problem. So we're working examples in related rates. Here's a good one. We got y x times y is equal to 5. So we've got our equation, and we want to find dy over dt when x is, let's say, equal to 3, and we are given dx over dt is equal to 2. All right, so we work with some small numbers here. So now let's take the derivative of this. So we have a product. We take the derivative of x and we get 1. But when we take the derivative of x, we have to write dx over dt times y plus, now we rewrite x, we take the derivative of y, that's 1. But when we take the derivative of y now, we write dy over dt. Taking the derivative of 5 is 0. Alright, now we have a new equation. So we're looking to find dy over dt when x is equal to 3. So we're going to plug 3 in for where there's an x, and then where there's dx over dt, we're going to plug a 2 in. So 2 is going to get plugged in right here, times y. Now we don't know what y is, but that's okay, we'll get to that here in just a second. Plus x is 3, dy over dt is what we want to find, and of course that's all equal to 0. Now this is all we're given here, dx over dt being 2 and x equal to 3. So to find what y is, what we're going to do is go back into our original equation, and we're going to plug x is equal to 3. We're going to plug 3 into this and solve for y. So let's just do that right over here. So we end up saying 3 times y is equal to 5. Therefore, y is equal to 5/3. So now we can plug 5/3 in right here. So we have 2 times 5/3 plus 3, and dy over dt is equal to 0. So now we just solve for dy over dt. So this becomes 10/3. I'm going to take it to the other side. So we have 3 times dy over dt is equal to negative 10/3. Right, it's positive. Take it over the other side of the equal sign, it becomes negative. Now I'm going to multiply both sides by 1/3. So we end up with dy over dt is equal to negative 10/9. If I multiply this side by 1/3, this side by 1/3, right, we get negative 10/9. So dy over dt is equal to negative 10/9. Nice. So we're working some examples in this topic, related rates. Okay, so here's going to be a famous equation that we use, and we'll be using this in an application problem. So we have x squared plus y squared is equal to 25, and we want to find dy over dt. So we'll write that right here. This is what we're looking to find, dy over dt, and we're going to be given x is equal to 3 and y is going to be equal to 4. And dx over dt is going to be equal to 8. So let's find dy over dt. Now this time we're actually given y, but in these application problems coming up, we won't be given what y is, so we'll have to find that. But that's okay. So we take the derivative of x squared and we get 2x. But now remember, we have to write dx over dt next to it, plus, then we take the derivative of y squared, so that's 2y, and we want to write dy over dt next to it. And of course the derivative of 25 is 0. Now all we have to do is just plug in, write the stuff that were given to us. So we have 2, x is 3, dx over dt is 8, plus 2, y is 4, and dy over dt is what we're looking for. So now it's just basically do some algebra, solve for dy over dt here. So we have 2 times 3 is 6, and 6 times 8 is 48, plus 8, and dy over dt is equal to 0. Now we're going to go ahead and take this 48 over to the other side. So we have dy over dt, and of course this is 8, is equal to negative 48. And then of course we multiply both sides by 1 over 8, right, to isolate the dy over dt. So now we have dy over dt, sorry that looks like a g there, but it's a y. And then of course 8 goes into 48 6 times, right? Okay. And there you have it. Alright, in this problem here, this is going to be kind of a semi-application problem. We're going to be looking at y is equal to x squared plus 1, and we're going to be wanting to find dy over dt, but at these particular specified values, when x is equal to negative 1, right, we'll have a unique dy dt. When x is equal to 0, then we're going to find dy dt, and when x is equal to 1, we're going to find dy dt. And dx over dt is staying constant here, and this time I'm going to attach some units. This is 2 centimeters per second. Okay, so we're going to have a point that's traveling along this graph, and of course the best thing to do is actually take a look at the graph. So I should note here that I plugged this into the address bar in the Google search on Google Chrome, and I got this graph to come up. This is Google's actual graph, graphing utility. Anyway, so here's the point, and this is actually nice to look at because we're talking about a point that's moving along the graph, and what we're going to be given is we're going to be given the rate at which we're traveling just in the x direction. So if you look at my cursor here on the number line, this is in the dx over dt. That's going to be our rate, but we're traveling just in the x direction, so we're traveling just horizontally, okay, at the rate I'm going to be giving you. And what we're going to be finding is the rate at which we're traveling just in the y direction, okay. So I don't know, does that make any sense to you? Let's look at the math. So the math is going to be easy to follow. Maybe understand what's actually going on about this point. Traveling along the graph might be just a little bit more difficult to try to figure out what's going on with that. But what I want to do is I want to find dy over dt when x is equal to negative 1. Okay, so I'm going to go ahead and find dy over dt. And that's easy enough because derivative of y is 1, then we write dy over dt. Derivative of x squared is 2x. And then I'm going to write dx over dt next to it. And of course the derivative of 1 is 0. So this is what we're going to be working with right here. So when x is equal to -1, what is dy over dt? Now this stays a constant here. So let's look at this. We have 2 times -1, and dx over dt is 2. And so this is going to end up being, what do we got here? -4. So dy over dt, so this rate is decreasing. So dy over dt is equal to -4. Now let's just go ahead and plug in the rest of these values here and talk about what's going on after the fact. Dy over dt is going to be equal to, now we're plugging 0 in, and of course if you were to plug 0 into this you would just get 0 out, right? So that means that dy over dt is 0, right? And one more, let's just go ahead and write it here. Dy over dt is equal to 2 times 1 times 2, and that's a +4 right here, +4. So the rate is positive. And we could say actually that it's increasing here and decreasing here because this is negative. The rate is decreasing, then it's going to 0, and then it's increasing. Let's see if I can attempt to actually draw this graph here. It's hard to write on these tablets. This is actually a bamboo tablet. It's connected into my USB port on my laptop. Okay, so the let's see, that graph looks something like this. Okay. Anyway. Okay. And we were looking at 0. And we'll say that this is 1. And we'll say this is -1 here. So I've sketched out this graph. Now, okay, let's see. This is 1, about right here. Alright, this is what we're looking at. We were moving in the x direction, and I'm going to plot an arrow. This is kind of like a vector here. 2 centimeters per second. But in the y direction, we are moving twice that. So I'm going to make this vector here about twice as long, or try to make it twice as long. 4 centimeters per second. Okay, and of course here, right at this point here, we're still moving in the x direction, 2 centimeters per second, but in the y direction we're moving 0 centimeters per second. Okay, because we're not going upward, we're not moving right north. But then as I move along this curve, as you can see what's going to happen here, as I continue to move 2 centimeters per second in the x direction, stays constant, what's going to happen to this number? Well, this number here is going to increase, right? This number is going to increase. Okay, so a little bit of an application problem. I guess we can go back and look at the graph again real quick. Alright, so I'm going to stay my cursor moving in this direction, constant at 2 centimeters per second. And what's actually happening in the y direction, this thing is actually speeding up. It's moving fast, isn't it? Okay, enough of that. Let's get busy with another problem. Alright, so this is going to be a little different. Of course, I'm going to attempt to draw something over here. This is the origin of the graph, and this is just some point on the graph. I'll Pick another point. I'm going to draw a straight line and draw another, attempt to draw another straight line there. Okay. This is what we're working with. We're working with, once again, I think just like in the last problem, y is equal to x squared plus 1. And we're given dx over dt is equal to 2 centimeters per second again. So 2 centimeters per second. Okay, in this particular one here, we want to find the rate of change. So we want to find the rate of change, right? So when you hear rate of change, we're talking about related rate problems. That's kind of like a key word there, rate of change. We want to find the rate of change of the distance between the origin and a moving point on the graph. So between the origin here and some moving point, we're wanting to find what is the rate of change of this distance, as you can see here. Okay, the rate of change of the distance between the origin and some moving point. There's a point moving along the graph here. So this is the path, and we want to find the rate of change of this distance. However, we're only given dx over dt. So what we're going to be finding is the rate of change. We're going to be finding dy over dt. And it's going to be just in a general sense. In other words, we're just going to have some x's over here. Okay, we're going to take the derivative of this, and we want to find dy over dt between this and the origin, right? So we need to come up with an equation that describes the relationship, right? This distance right here. We got to find an equation that gives the distance between this point and this point right here, right? So we know that the origin is 0, 0. And we know what the point here on the graph is. So this is going to be a case when we have to construct a formula that gives us the distance between the origin and a point on the graph. And so I said that this point right here is 0, 0, and then the point on the graph is going to end up being x, right? That's our some x value here. And then our y, right, is going to be x squared plus 1. So the y is x squared plus 1. Now, what we need to do is find the distance, right, between this point and the point on the graph, and that means that we're going to use the distance formula. And instead of writing d, I'm going to write r here. Okay, so that's going to be r squared is equal to the difference between x minus 0, so this is x minus 0, so this is the distance formula here, plus, and then the distance, right, between this point here, or the y values, so we're going to say x squared plus 1 minus 0, and square that. Now I'm not using a d here, and the reason for that is because of this d right here. Okay, so I'm just going to use r. So r, if we were to square root both sides, right, that would give us the distance, right, between the origin and some point on the graph. Okay, so what I'm going to do now is I'm just going to simplify this down, write those zeros, taking up space. So we have x squared plus, and then we're going to have x squared plus 1. And r squared. So now we want to take the derivative of this now. Okay, so the derivative of r squared is going to be 2r, and then I'm going to write dr over dt. Okay, dr over dt, that's what we're going to that's what we're trying to find, is equal to 2x times dx over dt plus, now I noticed I forgot to carry my power here. Okay, so bring the 2 out front, we write everything in parentheses, subtracting 1 from the power, and then taking the derivative of the inside and bringing it out, which is just 2x. But now remember, we have to write dx over dt. Now, we were given dx over dt, so we're going to substitute that dx over dt in, and that was 2 centimeters, so we're going to plug 2 in there. So we have 2 times r times dr over dt is equal to 2 times 2 times d. Oh, whoops! I meant to put the meant to put the 2 in for dx over dt here. Okay, magic just happened there. Times 2 plus 2 times x squared plus 1 times 2 times x times 2, right? Substituting the dx over dt in for 2. Now all we want to do in this problem now is solve for dr over dt. And of course, we have a 2 here. We got a lot of 2's going on in here, don't we? If I just go ahead and multiply through by half to everything here, we're going to end up with an r and then a dr over dt. Multiply that by half, we'll just be left with 2x. Plus, multiply all this stuff by half, we're going to get rid of one of these 2's here, and that's going to become a 4x times x squared plus 1. Okay. And now we have dr over dt is equal to, and you can go ahead and multiply this stuff inside, so that's going to become a 4x cubed and plus 4x, and then plus 2x is plus 6x. How's that? And it's all over r. So what is r? Right? If we go back up into the top here, what we're going to want to do here is square root both sides, so we can just isolate r, right? So if I square rooted this and square rooted this side right here, right? And so now what I'm going to do is just rewrite this dr over dt is equal to okay, I noticed something once again. Man, that was x to the first times x squared is x cubed, so that should be an x cubed right there. So let's take care of that. Alright, and okay, so I'm going to rewrite this. This is 4x cubed plus 6x over, well, that was a straight line, wasn't it? And it is just difficult to write on these tablets. And so down here would be the x squared plus x squared plus 1. Quantity squared. Now you can go ahead and multiply all this out if you want. You could even factor out a 2 out of the top, but I'm going to leave it like it is. So dr over dt is equal to 4x cubed plus 6x over the square root of x squared plus 1 quantity squared. Alright, so in this particular case here, we didn't actually, our answer wasn't just a number, it was actually, we ended up with an equation here with some independent, an independent variable here. So we ended up with actually a function, I guess you could say. Anyway, the relationship between dr over dt and x. I suppose you want to talk about that, but you can graph this and kind of take a look at what we got. Alright, so let's move on to some more examples. Alright, in this problem here we're going to be focusing on a circle. And we're going to have a circle here and with the radius of 6 centimeters. And we want to know, how do we find the area of a circle? Well, remember that the area of a circle is A is equal to pi r squared. Now what's going to be happening here is this circle is, let's say we started out with a circle of this size right here and the circle started growing. Okay, in other words, the radius was increasing, and actually the radius, we'll go ahead and write this down, the radius is increasing at 3 centimeters per second. Seems like I've used that before, but anyway, that's what we use. So the radius is growing at 3 centimeters per second. Okay, how fast is the area growing? So we want to know, what is dA over dt? That's what we're going to want to know when the radius is 6 centimeters. Okay, how fast is the area growing? So what we're going to want to do over here is we want to take the derivative. So we're going to have dA over dt is equal to 2 pi r dr over dt. So this is just a matter of now just plugging our numbers in. So we have 2 pi times the radius, so we got r, which is 6, and dr over dt, we're given that, and that is 3 centimeters per second. Now it is also I guess important that maybe we should write in our units here. So this would be 6 centimeters. Let me kind of sneak it in right there, okay? And then this is dA over dt, and I'll explain to you why we should probably write that in there. So now what we're going to do is just do the arithmetic. So we have 2 times 6 times 3. Alright. So what is that? 36? Alright. 6 times 3 is 18. 36. Okay. 36. Now we had a centimeters times a centimeters. So that's going to be a centimeters squared, and of course we just rewrite our seconds down here, and that was the reason why I wrote in the centimeters, wrote in our units. So this way, because we were given units, our final answer needs to be in some units here, and writing our units in helps us remember, you know, what our final units need to be. Right, centimeters times centimeters is centimeters squared over seconds. So this is how fast the area is changing with respect to time. How fast the area is changing with respect to time.